In the previous video, we introduced what imaginary units are and how they are used in the scope of complex algebra. In this video, we're actually going to start doing some complex algebra by defining what a complex number is and doing some basic operations with them. So a complex number is any number that can be written in the form of a plus bi. A here is our real number, and B here is our imaginary number, and it's imaginary since it's attached to the imaginary unit. This is probably the most important thing you would learn in complex variables, because it's like the one algebra technique you'll need to do when evaluating real numbers. Right here, yep, they say A is the real part and B is the imaginary part. So in this example of 4 plus 3i, 4 here would be the real part, and 3 here would be the imaginary part. There is also a similar definition for a complex number. There's actually a few definitions for a complex number. We could either have e to the ri, which is then equal to cosine theta plus I sine theta. Actually, I think it's r e to the I theta. Cosine here is synonymous with our real part, and sine here is synonymous with our imaginary part. So even in complex numbers, there is a trig and exponential relation to the standard a plus bi. Now we'll talk about the first simple operation when doing complex variables, which is taking a complex conjugate. Often in complex complex algebra, we denote a real number as z. So we'll say like z is equal to a plus bi. To take the conjugate means to just flip whatever sign is in the middle of your complex or of your real number. So if I have real number z is equal to a plus bi, then I have the conjugate of z, which we'll like call z bar, is equal to a minus bi. And it has a very similar property to real number conjugates, where if you multiply two conjugates together, you just get a product that looks like this, like a squared plus b squared. That's very similar to normal numbers as well. So without going through the proof, we can say something like if you had z is equal to 2 plus 3i and the conjugate of z is equal to 2 minus 3i, and you multiply them together, then what you have is the two real numbers squared added together to get you 13. So a useful tool, again, to know when you're evaluating real numbers and complex numbers within the scope of complex variables in algebra. So let's do a couple algebraic examples of complex numbers. The only rule when simplifying complex numbers is that real numbers can add together and imaginary numbers can add together. The real numbers cannot add with imaginary numbers. So if there's an I attached to them, they can add to something that has an I attached to it. But other than that, they would not add. So if I'm expanding this, I would have 3 plus 4 over here, and then plus 4i minus 5i. So I would think that this example evaluates to 7 minus I. Similarly for this one, again, I'm only grouping real numbers together and keeping imaginary numbers together. So this would end up being 3 minus 4 plus 4I plus 5I. So it'd be negative 1 plus 9I. So I think for example 3, you should be able to try that out on your own and see what you get before we check and see if our answers are correct. Example 4 is the next algebraic example that has some interesting steps associated with it. The problem with simplifying example 4 is that we have an imaginary number, and honestly, like a negative number, no doubt, in the denominator, which is something that we typically don't want to deal with. So this is also true for regular mathematics to deal with complicated denominators, whether they be, square roots or negative pairs of numbers. We would simplify this by multiplying the top and bottom by its conjugate. So if I have 3 plus 4I on the top and 4 minus 5I on the bottom, then to simplify the denominator, I'll multiply the top and bottom by the conjugate of the denominator, which is 4 plus 5I. As we learned in the previous slide, we know that when we multiply conjugates together, it ends up just being the two numbers of the two real numbers squared added together. So in the denominator, I know that this is just going to be 4 squared, which is 16, plus 5 squared, which is 25. So I got 16 plus 25 in the denominator. The numerator, we can multiply and evaluate this out. So I get 12 plus 15I plus 16I plus 20I squared. So unlike adding complex numbers together, when you can multiply complex numbers together. So when simplifying the numerator, I am just multiplying these normally, because I still end up with just one complex number and one real number. Because as you will see right here, I have now I squared, which we know I squared is just -1. So now what I have is 12 minus 20. So I have -8 up in the top. I have 15 plus 16, so plus 31I all over 16 plus 25, which is Yeah, sure. All right. So let's go through and see the answers on these examples and see how well we did. Nice. So as we had did on the first two examples, when adding 3 and 4 together, you get 7. And then when you subtract 4 by 5, so you have 7 minus I for the first one, -1 plus 9i for the second one. We got all that hunky-dory. Oh, the third one had you multiply them. Yeah, I should have done this one for you. So when you the third one tested that whole point where I just made, and the second one where when you multiply complex numbers together, you can multiply them normally. So 3 times 4 ends up giving 12. And then I got -15 plus 16i minus 20 times I squared. I squared here is -1. So I actually have 12 plus 20. And example 3, which gets me 32. And then I have -15 plus 16 to give me I. So I have 32 plus I for example 3. And it looks like we were right on example 4. The only way to simplify that truly is to multiply the top and bottom by the conjugate of the denominator. When we do that, we get 16 plus 25 and then the denominator, which gives us 41, sorry. And then in the numerator, we have 12 plus 15i plus 16i plus 20i squared. 20i squared again turns into -20. So I have 12 minus 20, which gives me -8. And then I have 15 plus 16, which gives me 31i. All right. Sweet. We got it. Hopefully the step-by-step process and the algebraic rules are starting to make sense for you in the scope of complex algebra.